Everyone, huge news today about the number 29 in mathematics, and specifically in number theory. Just yesterday, it was announced that Noam Elkies and Seth Claxburn have found an elliptic curve defined over the rationals whose rank is 29, and that is amazing. Let me explain what this means. An elliptic curve is an equation, what we call a Diophantine equation in number theory, and they are given by cubic equations of this form. And the goal is to try to find all the points, rational points on the elliptic curve. That means finding all the pairs xy of rational numbers that satisfy the equation. This is actually a very difficult problem in general, but there is something that helps us in doing so, which is the Mordell-Weil theorem. The Mordell-Weil theorem says that the rational points can be given the structure of a group, and in fact, that group is finitely generated. It's a finitely generated abelian group. And that means, by a theorem in abstract algebra, that there is a finite number of points of finite order, and then there is a finite number of points of infinite order that generate the rest of the points on the curve. That number of points is what we call the rank of the elliptic curve, and that is a very mysterious object. And one of the big questions in number theory is, what are the possible values for the rank? And nobody knows. But some of us think that those ranks can be arbitrarily large, and some mathematicians think that those ranks are actually bounded. A group of mathematicians, or four mathematicians, recently actually conjectured or gave a heuristic argument for the boundedness of the ranks, and they said that there are infinitely many elliptic curves with ranks up to 21, but after 21, there's only finitely many elliptic curves with rank 22 or higher. So there is a maximum rank that happens over all the elliptic curves over Q. And the question is that right? However, we know that there are ranks higher than 21. There was a discovery of an elliptic curve of rank 22 in 1997, rank 23 in 98, rank 24, rank 28 in 2006. And since we had not found any elliptic curve of rank higher than 28, and just yesterday, there was an announcement of an elliptic curve of rank 29. So that has broken the record. And just to give you an idea of how much of an accomplishment is to find such a curve, this is the equation of the curve that has that rank. The rank is so large that we can't even prove that the rank is exactly 29. If the rank is at least 29, and these are the coefficients, look how large the coefficients are, of 29 points that are linearly independent and generate a subgroup of rank 29. In fact, if we use the generalized Riemann hypothesis, then apparently the authors can prove that their rank is exactly 29. Maybe here you can see a little bit better some of the coefficients that go into the definition of this elliptic curve. It's massive. Now, is this evidence that the ranks of elliptic curves are unbounded? Hardly. Imagine that the ranks can be arbitrarily large, but the largest we know is 29. Well, what we think is that those elliptic curves with higher and higher ranks are going to be extremely difficult to find computationally. They are very sparse. There are very, very large coefficients on those elliptic curves. So it's just a matter of our computational power increasing, or really some very good ideas to construct elliptic curves of higher and higher ranks. But some of us think that they are out there.